Hello everyone, and we are starting to close in on the end of the course, and one thing we have not yet thought about is electron spin. And what is electron spin? Well, in 1922, Otto Stern and Walter Gerlach passed a bunch of silver atoms through an inhomogeneous magnetic field, and they came across some rather unexpected results. As we know, the silver atom has an electron configuration of 4d10 and 5s1. And what this inhomogeneous field did was it applied a translational force to the magnetic dipoles. There weren't expected to be any magnetic dipoles, but it turned out that the beam of silver atoms was split into two. No one could really understand what was going on at the time. So I'll give you a little bit of a potted history as to how people came up with the idea of electron spin, and also how there's no classical equivalent to electron spin, and we'll think about why that is. So the section heading here is an electron has an intrinsic spin angular momentum. And let's start by reviewing that Stern-Gerlach experiment. So this stream of silver atoms was passed through a magnetic field, and that stream was then split into two parts. So we have to think about why we get splitting, and this is analogous to the Zeeman effect. So quantum mechanically, a state with a given value of L would be restricted to split into 2L plus 1 discrete orientations. So why is this important? Well, the observed splitting in this case was that the beam was split into two. So let's think about those guidelines again for splitting. So 2L plus 1 is equal to 2 would suggest that L would be equal to half. And this presented some problems. It was definitely unexpected. So this is the observed splitting. And of course, these are the guidelines for splitting. Furthermore, in later years, high-resolution spectroscopy was used to demonstrate that a transition from n is equal to 2 to n equals 1 for a hydrogen atom left a signal that that transition line, that line associated with the transition, was actually split into two. In fact, a doublet. And there was no solution. Nobody knew really what was going on until in 1925, Pauli postulated that an electron could exist in two distinct states. And he, in an ad hoc way, that means really just because it was needed, so he introduced a fourth quantum number. And now this fourth quantum number is called the spin quantum number, and we'll label that as little m sub s, and it's restricted to values of plus or minus a half. So let's try to summarize that over the next few lines. So yes, Pauli introduced a fourth quantum number. So that is now called the spin quantum number. So Pauli did not give any interpretation to the fourth quantum number at the time, and it wasn't until Dutch scientists Uhlenbeck and Goudsmit in 1925 aligned these two intrinsic states and identified those two intrinsic states with two angular momenta states. We kind of know these as spin states today. So the only thing really we have to go on is that the inhomogeneous magnetic field split this stream of silver atoms, and so that magnetic moment of the silver atoms associated with the 5s1 electron was associated with angular momentum, as was seen for the Zeeman effect. In other words, it was the angular momentum of the electron that, when aligned with the magnetic field, led to the splitting. So just like we have the eigenvalue equations for the square of the operator for magnitude of angular momentum, of course we're very familiar with this expression, so I'm putting it up as a comparison. So just like we have this expression for angular momentum squared, of course we also have the operator for angular momentum in the z direction operating on that same spherical harmonic. So we have this m sub l h bar y l. This is the spherical harmonic again, the angular part of the wave function. So just like in this particular case, there were certain spin operators that were defined, and these spin operators that were defined were s hat squared and sz hat, and the eigenfunctions were given by alpha and beta. So let's have a look at what the associated equations are that compare with the equations, with the Schrödinger equations, with the operator equations that we've just looked at for angular momenta, for the spin, for the orbital angular momentum of the electron in the hydrogen atom. Let's think about now the spin angular momentum, this quantum number that's just been introduced for the electrons themselves. So we have some familiar looking expressions. This is lowercase s, and we also have the same essential equation, but now in terms of alpha and beta. And we have s is equal to a half in here, and we'll also recognize s sub z hat alpha equals plus 1/2 h bar alpha, and similarly sz for the wave function beta is equal to minus 1/2 h bar beta. So we must recognize as well, by the way, these are uppercase s's. What else do we get from this? Well, alpha is kind of like y to the half. To the half is like a spherical harmonic wave function, but really this is just, as the textbook says, a formal association. And I think most importantly, because s never assumes large values, so s, the highest it can go is a half, right? The magnitude of this little s is a half, okay? And so that value can never go higher than a half. And so because s never assumes these large values, because the observable, the spin, never ends up being larger than a half h bar, or the angular momentum in the z direction never exceeds 1/2 h bar for a particular electron, we never get these large values. We never get large values that you would see for other observables that we witness in quantum mechanics. And so for that very reason, spin never actually jumps to the classical level. We never get to a corollary. We never get to a comparable in the classical world. We say the spin angular momentum, s, uppercase S, is equal to h bar square root of s times s plus 1. So that's the observable s that we would see from our expression in the above equation. Spin is very hard to get your head around because there is no classical version of spin. So these wave functions, alpha and beta, these are eigenfunctions, and we assume that they are orthonormal. And what this means, in fact, is that alpha times alpha d sigma, so this is a new integral. Sigma is the spin variable, and that is equal to 1. Similarly, for the wave function beta in here, This is also equal to 1. And we have the orthogonality piece. So the normality piece is what we see here. And then, of course, we recognize that these expressions, because alpha and beta are orthogonal, are equivalent to 0. And that's spin for you. Spin basically is that ad hoc additional quantum number that we need to add into the atom. It tells us about how we place electrons. We can put 2 electrons in any one orbital, spin up and spin down.